Well, our next speaker this morning is Professor Nazneen Rahmanh, who is currently a Professor of Human Genetics at the Institute of Cancer Research. And she has the tremendous advantage of being both a doctor and a scientist. So let's give a warm welcome to Nazneen.
Good morning, and thank you very much for this invitation. The title of my talk is Genomic Medicine, Are We Answering the Right Questions? So it probably isn't a surprise to you that I don't think the answer to that is an unqualified yes. I don't think it's an unqualified no either. I think there have been extraordinary and wonderful advances in genomic medicine over the last quarter of the century, and particularly over the last 5 years, and we've heard about many of those from the last two speakers. But I do think it is a time, in fact I think it is the time for us to just step back a little bit, take stock, and think about whether we are asking the right questions and answering the right questions. And in part, I think that the reason that we have to do this is because genomic medicine at this time is exceptional. We often have advances in medicine, fortunately. We're often implementing change. But it's very, very unusual to have to implement a change of this kind of scale and magnitude in medicine. And we really do have to think about that carefully. So this is a slide from Illumina that they put out at the back end of 2014 about their predictions about how many genomes would be sequenced up to the end of 2017. I think it's a bit of an over-prediction, but in the right ballpark, and around about 3 million whole genomes is what they were predicting. If you think about the same period 10 years ago, it would probably be less than 100, certainly less than 1,000. So that's an extraordinary level of change, and we've heard about the opportunities that provides us in terms of bringing benefits to patients and people generally. But of course, the sequencing alone is only part of genomic medicine. In order to make genomic medicine work, you have a whole set of pathways and a whole set of processes that have to work. For the genetic test alone, the sequencing is only part of that process. You also have at least 2 other parts. We found the analogy of a book to be quite helpful in sort of articulating this. So when you're making a book, you obviously need the letters, and that's equivalent to your sequencing, but having a random string of letters isn't going to take you very far. You have to do a sort of analysis and get them in the right words, in the right paragraphs, with the right punctuation. And it's only after that you've sorted that out that you can actually read it and understand its meaning, if you know the language. And it's only then that you can actually think about the actions that you might actually implement. So the genetic test is quite complex, and the sequencing alone is only going to get you a very small part of the way. But in terms of genomic medicine, we also have to implement that. So you need to have at both ends some kind of interface between your doctor and your patient so that you can get a sample in to do the test in the first place, and so you have an appropriate process to actually implement the actions. So to make genomic medicine work, we have to make all of this process work. Now, for most of the last 25 years, the bottleneck in this process was at the sequencing. That was the rate-limiting step. And what the advance in the sequencing technology does is it completely obliterated and removed this bottleneck. But unfortunately, what usually happens is that you don't remove bottlenecks, you just move them somewhere else in the process, and that's obviously exactly what has happened. And so now what we have to do is to try to sort of remove and alter these bottlenecks, because the sequencing bottleneck has been removed. So the question that people traditionally sort of ask is, how do we upscale the clinical pathways, these other parts of the processes, to accommodate the extraordinary advance in genome sequencing? And I think that's the wrong question to ask. I think it's a kind of doomed question to ask. The question that we have to ask is, how do we create sort of radical, innovative clinical pathways to complement the extraordinary advance in genome sequencing? And the reason we have to think about it in this way is, I'll try to exemplify using an analogy of transport. So if you think about sequencing in terms of types of transport, the old ways in which we used to do sequencing was equivalent to kind of hobbling around on sticks. and now with the next generation sequencing, we can suddenly travel by rocket, and it has been extraordinary. Things that used to take us years, we can now do in hours. But this adds a lot of pressure to our transport infrastructure. So if you should imagine if we were trying to get from the tube station to here by walking, but now suddenly we're travelling by rocket, that's going to put a lot of pressure on those systems. And the one thing you know isn't going to work is just widening the pavements. That is never going to allow you to accommodate your rocket travel. We're going to have to think of completely different ways of trying to accommodate this amazing increase in sequencing. So I think with respect to the analysis, quite early on, people did realise that the way we used to handle small numbers of sequencers compared to millions of sequencers isn't going to work. And I think by and large, a few little nuances that need to be sorted out, that bit has been sorted out. But with respect to the interpretation and the implementation, traditionally, what's largely been happening is that we've been trying to upscale the systems that we had before to try and accommodate the new amount of sequencing, and that's not working very well. So I'm just going to articulate that a little bit more and give some sort of suggestions of ways in which you can potentially have more radical changes to complement this change in sequencing. So this is a sort of traditional process of interpretation. The key aspect about it is that it's an individual variant process. Each individual variant comes into the process and is somehow tries to be categorized. And largely the way in which people are trying to classify that is relatively binary. Is it pathogenic or is it not pathogenic? And there are all sorts of problems in this system, but when it was a low scale, there wasn't very much testing being done. It was possible to do that in the clinical setting. But effectively what happens is you get lots of different variants. Each individual variant is often subjected to a whole set of in silico tools, none of which in fact robustly predict the clinical effect. After that, all of these variants get put into these different bins, but most of them end up in this uncertain, this VUS category, and that's partly because it's the largest category. Anything between 5% and 95% gets into that category, and it's partly because these tools aren't very effective. But effectively what you've done here is you've got all your variants, you spend a lot of time and effort, and then you end up in the same place. They were uncertain before and they're uncertain afterwards. But an even bigger problem is that's where it stops, and the actual what you do with them in the clinic is sort of left sort of separate and sort of in sort of an ad hoc way. In the sort of clinical MDT, people will make sort of decisions based on this uncertainty. So that is not an optimal situation, and if nothing else, leads to inconsistency in how we're managing these variants. What we need, and what we need as soon as possible really, is interpretation pathways that will allow you to have high throughput, large volume, fast turnaround, and has clarity that's intelligible and usable by non-experts and patients. So what we need to do is to go from this to something like this. We urgently need innovative approaches for delivering variant interpretation for clinical use. So how might one do that? Well, I think one of the things that is absolutely crucial if you're going to try and triage things into clinical action groups is that you have to define those clinical actions in the first place. So that's going to be different for different diseases, different genes, but for every single variant and every single gene and every single disease, there will at least be one action group where you would manage that variant as not clinically relevant. You will always have variants in that class. And in fact, what you can and should do, because we know that we all have thousands and thousands of variants, is that all your variants should start off in this class. So, and then you would make explicit criteria that would triage them into some kind of action groups. And this is a sort of, on one level, it's a sort of deceptively simple change to the process that on the ground has dramatic consequences and makes things much, much easier. So instead of having each individual variant coming in and trying to put it into particular groups, they all start off as being innocent until proven guilty, and your onus is then to explicitly outline the criteria that are going to move them out into that group, out into another action group. And one of the other things that it allows you to do, in fact it forces you to do, is to move from just taking one individual variant and thinking that impact on the phenotype, and bringing into those decision trees all of the different types of information that we do in that ad hoc way when we're trying to work out the clinical impact. Things like what's the mechanism of pathogenicity. If a mutation in a gene is inactivated in order to cause a disease, you're going to interpret variants in that gene differently from ones in which it's activated to cause that disease. And that obviously makes sense, but we actually don't put that in the sort of front end of it. We leave it until afterwards. In this sort of process, what you're doing is you're taking all of that gene-based and phenotypic information and you're using it to set your criteria so that you can explicitly articulate how you move from being not pathogenic into pathogenic. So how does it work in practice? We found that it works very well. So I'm going to use as exemplars for some of the things that we've been doing the BRCA genes, BRCA1 and BRCA2. These are good genes to use as exemplars, partly because to date I haven't found any situation in genomic medicine where one or other or both of these genes isn't a good exemplar, and that's for the good, the bad and the ugly. So they're also clinically highly relevant, both in terms of diagnosis and prevention, and they're also very well known in part because of their patronage from a certain Hollywood movie star. So the BRCA genes are, so the other reason that they're also very good examples is that everyone has to deal with them, because variation in the BRCA genes is very, very common. So if you're handling any kind of data from exomes or genomes, you will have BRCA variants that you have to triage. And that applies even to very rare variants. So we've done some sequencing of population individuals from the UK, and about 10% of the healthy population will have a rare BRCA non-synonymous or missense variant. And these are exactly the type that are called VUSs. So these are common collectively, individually rare, but collectively common, and therefore people are having to deal with them. So what should be the management of those kinds of rare variants? Well, the fact that they're present in 10% of the healthy population alone shows that they can't all be pathogenic. And in fact, there's an abundance of information that shows that you should manage rare BRCA variants in the same way that you manage a negative BRCA test. It shouldn't be used in cancer management, it shouldn't be used for cancer risk prediction in relatives. What actually happens is much more inconsistent, and part that's just because intuitively, if you've got a single report, a single patient and a single doctor, and it's got a variant of uncertain significance, it's a loaded term. People sort of tend to think of it as being guilty until proven innocent, and so people start doing actions upon that. And these can be very major actions that people do, and particularly in the States, and there have been a couple of papers from the States which saying that about 30% of entirely healthy, well women will have their breasts removed on the basis of a rare variant. So you can see that given this is present in 10% of the population, and there's all the evidence suggests that they're not going to be pathogenic, that this is potentially giving very significant harms at a patient level and very significant burdens to our health services on a societal level. So the question then people are asking is which BRCA variants are pathogenic? And in fact, the evidence from the last 20 years have shown really very clearly that well over 95% of the pathogenic BRCA mutations lead to premature truncation, well over 95% of truncating mutations are pathogenic, and well over 95% of non-truncating variants are not pathogenic. In terms of the genes in the genome, the BRCA genes are actually at the easier end of the spectrum in terms of how we interpret how variation is impacting phenotypes. And in fact, the pathogenic non-truncating BRCA mutations are very rare, and they are in key domains. So with this knowledge about the gene base, the gene structure, the variation, it actually allows us to relatively easy set these criteria. So we have variants. Every time we do a test, we do about 100 tests of cancer panels a week, and we will always get variation in the BRCA genes, but most of those are explicitly in the blue. They stay in the blue. There are no other variants that need to be triaged up, and they can go straight out into the clinical report.
We've got very clear criteria, for example, all truncating mutations, bar a few exceptions that allow it goes up to red in terms of pathogenic mutations. And then there's usually a handful of variants that we have to have hand curation each week. Most of those, and often all of those, we can then triage out into red and blue relatively straightforwardly. It takes me maybe about 15 minutes. And then very occasionally, less than 1% of the time, there is a variant there that needs some other specific evaluation. For example, it's predicted to affect splicing. We need to do a splicing assay to sort that out. But it works very well, it's fast, it's consistent, and we can get automated interpretations for well over 95% of those variants. And it applies to other genes as well. Now, of course, sometimes you need to have an iterative process. Sometimes you might get a change in your variant interpretation because new information becomes available. You want that to happen very, very rarely and hopefully never in terms of changing something from a red variant back down to blue. You don't want to change something being pathogenic and now say it's not. But you will get some that will be blue, but you get some more information, and then you can say now it is pathogenic, and you can go back to the patient and give them new information. But it actually doesn't happen very often. So it is the case when we're doing these sequences that every variant has to be triaged into a clinical management category. But it is possible, with a little bit of sort of creative thinking about what we're trying to do and thinking about these processes afresh, to have automatic interpretation, I think for well over 95%, we probably will be able to get to 98% across the whole of the exome. The ones that are left are going to need really expert hand curation, people who know genes, who know the phenotypes, who know those diseases, and you are going to have to need some ongoing iteration. But it is possible. But there are some other problems, and there are some other questions that start to become known as you're going through this process. One of the questions that gets asked a lot, and we don't question it enough, is this question. Traditionally, what we're asking is the variant pathogenic or non-pathogenic? We're really very binary about that. And that's not giving us enough nuance in that question. What we need to do is ask a much more nuanced question. What is the potential human impact of the variant? And we're really at the very beginning of this. We haven't really even got the sort of lexicon, the language to sort of describe those different nuances. But it's really, really important, because the way in which genotypes and phenotypes can impact is very complicated. And again, the BRCA genes can exemplify this. So a specific mutation in BRCA can confer very different risks of different cancers. So they confer pretty high risks of breast and ovarian cancer, small risks of prostate and pancreatic cancers. Different BRCA mutations confer different risks of a particular cancer. So in fact, mutations in the middle of BRCA2 have different risks of breast and ovarian cancer compared to either end, though we don't actually put that into our risk-giving sort of algorithms currently. Most sort of, I suppose, counterintuitively and most challengingly, a specific BRCA mutation can confer different risks of a particular cancer in different contexts. So, and these things can have really big impacts, particularly as people are doing more and more sequencing without knowledge of them. So one of the things that increasingly is happening is people think, oh, I've got somebody with cancer and they've got a pathogenic mutation in BRCA, therefore BRCA is called their cancer, let's give them PARP inhibitors, etc., etc. And that's a pretty seductive way of thinking. But cancer is very common. 1 in 3 people will have cancer. BRCA mutations are not so uncommon. About 1 in 250 people have a BRCA mutation. So those things are going to come together just by chance. And if it's not breast and ovarian cancer, usually that BRCA mutation is not causally related to the BRCA mutation. It's just because cancer is common. So this is just one bit of data just to show that. This is the data from the TCGA, where there are over 7,000 sequences from 28 different cancer types. Amongst those, there are 158 that have a pathogenic mutation in BRCA. But as you can see here, the first 2 are breast and ovarian, very significantly associated. And here, those mutations are causally related to those breast and ovarian cancers. But for all the other cancer types, what you're just seeing is just the population frequency of BRCA mutations in that population. And in those cases, they're not causally related, or it's very, very unlikely that they're causally related. but people are sort of not aware of that. They think BRCA cancer must be related. So we need to be aware of this. As I said, this issue about the impact of the mutation being dependent on the context is something, again, that people are very unaware with. So generally, when people are saying what's the risk of a BRCA mutation given cancer, often people will say, oh, it's 80%. And they will say it's 80% irrespective of how that mutation has been identified. And that data comes from the initial discovery of BRCA, which was in families with lots of cases of breast and ovarian cancer. So they're really high cancer clusters. And within the context of a strong family history of breast and ovarian cancer, it is true that a BRCA mutation in that context has a high risk, approaching a lifetime risk around 80%. And that is primarily due to the BRCA mutation, but there's also a whole load of other things, most of which are unknown to us, that are also having an impact in that context. What we know is if you, instead of looking at mutations that have been identified in people with a strong family history, you look at people who've got unselected breast cancer, so the relatives, the individuals in that context, so one individual with breast cancer. The risks in that context is much lower, only around about 40 to 50%. We don't exactly know why, but presumably the other factors that are potentially leading to this familial clustering are not also in this setting. But certainly in this setting, you shouldn't be really using the 80%. You should be using it appropriate to the context in which we found it. What we don't know currently is what is the risk of cancer if you just randomly find a BRCA mutation in the general population, so-called incidental finding in that context, or through prenatal testing or whatever. We don't know. Those studies have never been done. What we do know is it can't be 80%. It can't be 80%. It quite possibly isn't even 40 to 50%. And so this is really important. These are well people you're potentially giving information, and most people, well, many people will have different choices if their risk is 80% compared to if it's 30%, particularly if the choices that they're thinking about is having surgical removal of parts of their body. So these are really important things that we have to be aware of and we have to try to address. And it leads me to, I think it's probably my second least favourite question that's asked at the moment. It wouldn't be politic for me to say what my top most favourite question is, but you can ask me afterwards. So this is a question that I'm asked all the time, which is, should we tell people about incidental findings? And the reason I find it frustrating, this particular question, is it's had a real impact on the whole field and how we're directing things. And I think there are two better questions that we should be asking before we ask this question. The first question, before you ask of your data or of anything that you should do, before you ask about the incidental findings, is look into your heart and soul and say, have you really sorted out the pertinent findings? Because I think there's a whole lot of things that we need to be dealing with and discussing with our patients around the pertinent findings before we move on to the incidental findings. Assuming we have all done that, and it is obviously these additional incidental findings are of interest, the key question is not should we tell them, it's what should we tell them, what can we tell them? So generally when people are asking these questions, and when we ask people, do you want to know about this information, the assumption both from the people who are answering the question, and I think often from the people who are asking the question, is that the quality of that information is reasonable. You know, it's good information. If you ask people, do you want to have unreliable, inaccurate, bad information, I think that's different than if you ask people, would you like to have good information? And a lot of the time, we are not able to give people robust, accurate information. And unless we recognize that and we ask it in that way, we're not going to do the studies that we need to do in order to make sure that we are giving the correct information about the incidental findings. So I gave the example of the BRCA genes, but I could have actually, Alex, our first speaker, talked about the liquid biopsies and finding information in the blood. And that's actually another perfect exemplar of where information from one context is being applied in a different context, and we're not quite clear whether that's accurate. So in terms of if you've got a patient with cancer and you do a liquid biopsy that you're sort of monitoring how that cancer is progressing, that's working very well. If you're now taking an entirely well person and seeing if there may be some cancer cells, we actually don't know how many of those would just go away anyway, what the sort of normal prevalence is. We have seen extraordinary advances in early detection, but we've also seen that quite a part of that, at least, is due to overdiagnosis. You're picking up things that would never have become cancer in the first place. So we have to be really careful in terms of how we're doing these in the future, that we're giving the correct information and not leading to overdiagnosis. I've no doubt Illumina and Grail will be thinking about that very carefully when they're selling their product. So have I got 5 minutes? Okay. So I'm just going to move on from interpretation to talk about implementation, which is another area where there's major bottlenecks and we need radical ways of thinking about things. So the question that typically gets us asked here is, how can we provide genetic counselling to everyone having a gene test? How can we upscale that niche area to sort of be provided to everyone, because everyone's going to need genome sequencing? So I think the question that we should be asking is, how do we provide the information people need to consent to and understand their gene test? And that seems a bit subtle, but actually it is a very different way of thinking about that information. And the reason we have to think about it this way, we have to sort of look back into how genetic counselling, why we even sort of have genetic counselling, why it's even called that. And the reason is that certainly for the cancer predisposition genes and for a lot of aspects of medicine, when we were doing these initial genetic tests, because it took such a long time to get the results and it costs a lot of money, we didn't do that at the sort of front line in terms of diagnosis and treating patients. Largely it was restricted to doing what we call predictive genetics. You're giving entirely well people information about things that may or may not happen in the future. And those are quite complicated and does need this so-called sort of counselling. In the context of when you're doing a test in a person who's ill, and it's really just a medical genetic test. Now, we do effectively counselling. It's not in a situation that in medicine that if it's genetics, a genetic test, we sort of talk to them and give them information so that they can make informed decisions. We do that ideally in every interaction with a patient. And actually, genomic medicine, genetic testing, genetic diagnoses happen routine in medicine all the time. Any genetic diagnosis that has a physical manifestation that you can diagnose by examining the patient has always been mainstream. It has always been done by whichever doctor first sees the patient, and often the doctor feels very pleased about making that diagnosis. So there isn't actually a necessity or even a precedence that all genetic diagnoses have to go through this process of genetic counselling. What it is, and is appropriate, is that if you're taking a well individual and you're trying to discuss about whether or not they want to have information about something that may or may not happen to them in the future, that involves careful kind of discussions. In a medical situation where you're trying to get information in order to give the person the correct treatment, that's just medicine, and we need to make sure that in order to serve predictive genetic testing, we are not compromising the care that we're giving to patients. So I think in moving forward, what we have to do is separate out these genetic information into the context of when we're doing it in medicine, and that should go into the medical structure, and when we're doing it in terms of prediction. So we've been implementing that for cancer testing at the Marsden, and it does work very well in practice. So what we now do in this mainstream model, if the genetic test is a medical test, i.e. in a cancer patient, that is happening through the trained cancer team. They're doing that. All the test results are interpreted by us so that we can give the clarity that I talked about earlier in the talk. If the person has a pathogenic mutation, they automatically have a genetics appointment with their result, so that the normal processes that happen when you have a mutation and helping the family, etc., can happen during the normal processes. If they don't have a mutation, then likely they're not going to need extra genetic input. That information can be used to give them stratify their treatment appropriately, but they're likely not needing to come to see us in genetics. And currently, anybody who's unaffected, a well individual trying to access this kind of predictive information is being done through genetics. So we've implemented that for the BRCA genes for both breast and ovarian cancer. The training is very simple. It takes about 20 minutes. It's based on short e-learning modules. You can read more about all of this program on the website at the bottom if you're interested. So I'm just going to show you our initial ovarian cancer data. So about 15% of ovarian cancer patients have germline mutations in BRCA, and we now offer BRCA testing to all individuals with non-mucinous ovarian cancer. And in this study, we offered it to 207 patients, and all of them wanted it. Every single person wanted it, and most of them agreed and wanted it on the first time that we talked to them about it. And that's quite important as well. There has been a change societally, particularly in the medical context, with people happy and wanting to access genetic information. About 16% of them had a BRCA mutation, and for those, the information was useful both for their cancer treatment and for their family management. And actually, for the people without a mutation, actually that information was helpful. In general, stratifying by status rather than just identifying people with mutations is what we should be aiming for. And the feedback has been positive, irrespective of whether there was a mutation or not, both from the patients and from the clinicians. And it's incredibly efficient and effective. The traditional method of genetic testing, there are about 5,000 patients that are eligible for testing, ovarian cancer patients in the UK, though currently very few of them are actually getting their testing simply because the genetic counselling capacity is not great enough. And that's because they would be seen in oncology, they'd have to be referred to genetics, they'd have an appointment before and afterwards, and then they'd go back to oncology. So it would take about 21 weeks, and for 5,000 patients, that's 10,000 genetic appointments. In the mainstreaming model, the oncologist or the cancer nurse specialist talks about them and does the test at week, the first time point. Our turnaround time is about 3 weeks, they get the result, and only the people with mutations, and one or two others, will come forward. So instead of having 10,000 genetic tests and taking 21 weeks, you now are taking under 4 weeks and only needing, genetic appointments, and only needing 750 genetic appointments. So just implementing this model would save the NHS about £2 million per year on genetic consultations alone. It would allow us to implement the NICE guidance, and most importantly, it gives flexibility to the patients. So patients can go to the genetics pathline if they want to, but they don't choose it, so they have the flexibility, and we're bringing more patient-centred care. So the take-home message is that the revolutionary change in sequencing requires of us to look with fresh eyes at all aspects of genomic medicine. And I think it's often forgotten that we have been doing genomic medicine for at least a quarter of a century. So there's a lot that we have been doing. We have to look about all of those processes. And we need to be equally creative and proactive in building these paradigm-shifting innovations to those clinical processes, both to maximise the benefits of the advances in genetic sequencing, but also equally importantly, to ensure that we minimise harms. Thank you very much.
Thank you, Nazneen. I'm sorry, we're not going to have time for questions right now, but I'm sure you're going to be around for some time, and we'll be happy to take the questions afterwards. That's lovely. Thank you very much. Thank you.